Hi, today I want to talk about filters and signal filtering. First, I would like to start with the simple fact that any signal could be approximated by a combination of sinusoidal waves of different amplitudes, phases, frequencies. Just to remind you, amplitude is the size of the sine wave. Phase is a shift from the origin, and frequency f is a reciprocal of the period p, which is period in time. So the more dense the sine is, the higher its frequency. Slowly changing waves are lower frequency, and faster changing waves are higher frequency. The representation of a signal as a sum of sinusoids is called Fourier series. The sum might have infinite number of terms and sine waves, but they have discrete frequencies. Typically, we describe amplitudes of different sine components as discrete spectrum, and this plot looks like that. When we use a continuum of frequencies, this representation is called the Fourier transform. The goal of filtering is to remove some of the signal components that we do not want, while leaving some other components as they are. Alright, there are four main types of filters available. LPF, which is low-pass filter, passes all low frequencies and blocks all of the higher frequencies. High-pass filter, or HPF, passes all higher frequencies but blocks all of the lower frequencies. Bandpass filter, BPF, passes frequencies in the middle of the spectrum but blocks lower and higher frequencies. Finally, band stop filter stops a chosen range of frequencies in the middle. If the stop band of these frequencies is narrow, people also call that filter notch filter. Combinations of these filters are also possible to use, and the ideal gains for these filters are shown in the slide. Also, ideally, we would like to have phase shift of all possible frequencies to be zero by the filter. Unfortunately, in practice, none of it is possible. Well, okay, so what we can achieve in practice? In practice, we need to define specifications for the pass band, stop band, acceptable ripple size, roll-off, slope, and so on. And we might get something like this. Not exactly ideal. Not exactly ideal gain or phase, right? There are two types of practical digital filters that could be implemented in the computer. One is called finite impulse response, or FIR, and another is called infinite impulse response, or IIR. There are also adaptive and nonlinear filters, but we will not talk about them in this micro lecture. The FIR is very simple to implement. It is just a weighted average or linear combination of a few present and previous signal samples. Here, y of n is the present filter output, and x of n is the present signal sample. X of n minus 1 is the previous signal sample, and so on. The order of this filter is the number of signal samples that you are taking into account. You might be familiar with the moving average filter, for example, which is FIR filter. Also, you might have heard about exponential smoothing, which is FIR filter. The IIR filters are more sophisticated, and they are typically represented by a generic transfer function. Please note that IIR filters use previously computed filtered values to compute the present filter output. Now let's compare FIR and IIR pros and cons. So, FIR filters are definitely easier and simpler to design and also to implement, since this is just weighted average of multiple numbers from your input. It is promised that it will always be stable, so there is no problem of stability, and the signal will never diverge and no matter what kind of filter you choose. Also, it's very easy to get linear phase with FIR filter, because if you decide on the symmetrical coefficients in that filter, you will get linear phase, and linear phase is good for multiple different applications, because if you know that your phase for different frequencies will increase linearly, you can predict exactly how many samples you need to delay your output to make it fit the real filtered output of the system. Now, you also will have less rounding errors, because you do not have any feedback loops in the implementation of that filter, and this means that you will not gain additional errors from the computation itself. But on the other hand, this FIR filter is computationally expensive. All FIR filters are computationally expensive, unfortunately. So it's more difficult to compute to the computer. It will take longer time for the same order of the model. Now, to get same performance like IIR filter, you will clearly need much higher order of the system, which means you will need to take much longer history in your coefficients. And in that sense, typically for FIR filters, you need very long signals to be processed. Short signals are not processed well by FIR filters. On the other hand, infinite impulse response filters, which are IR filters, are much better in terms of performance for the same order of the system. You can get gain flatness, you can get good roll-off, you can get stop band gain better than FIR filter, and so on with lower order. Here you can see example of a few popular filters of IIR type. You have Butterworth filter, which is maximally flat frequency response. You do not see any ripple, not on the initial gain 1 band, which is passing band, not after the stopping band. But you have much better characteristic for Chebyshev filters because they are much closer to the ideal shape of the filters that we discussed before. Now, these ideal shapes could be flat, then straight line, and again flat. So Chebyshev is the closest one to that type of shape. But it has some sort of ripples at the passing band or at the stopping band. Now, you have also steepest cutoff filter, which is elliptical filter. And this filter is also having some sort of ripple both on the passing band and stopping band. Matlab has multiple different functions to filter different signals. You have standard function which is called filter, and you can put coefficients of B and A that we discussed in the FIR and IIR filters here, where X will be the input and Y will be the output of the filtered signal. Then you have also function filt, which is zero phase filtering, and this filter is running in one direction first, and then it's running in the other direction first, and then the result is the average of filtering in one direction and other direction. So the phase will be fixed in such a way that you will not have any phase changes by the filter. So the advantage of that type of filter, which is filt, is that you have zero phase, close to the ideal one. But the disadvantage of that filter is that if you have signal which is changing from left to right in time, you might introduce additional artifacts which are before the zero time. Because when it will be filtering backwards, it will introduce some sort of other things from zero time backwards. Now you have also another type of filter which is FFT, fast Fourier transform based filter, and this filter is designed only for FIR filters. So you need only coefficients B, you do not need any coefficients of A in that filter. Again, X is input, Y is output of that filter. Now, a few years back, Matlab introduced functions which are called low pass, high pass, band stop, and there you can get automatically designed filter for your needs. So you just define what passing range or stopping range you want for your filter, your sampling frequency f of s, your input x, and it will do for you all of that magic of designing filter and filtering your signal and returning the output at y. The problem with that approach is that you cannot easily learn what kind of filter is used here, what parameters of the filter were used. Though you can play with the parameters and you can adjust them and you can decide what parameters you want inside of that function with additional parameters, but people typically use just those basic parameters, and then it automatically decides if you will need FIR of the lowest order or IIR of lowest order. It could be Chebyshev or something else. So it's better to know what parameters you're using and why it has chosen particular set of parameters for your needs. It might be good for you or might be bad for you. Now, just additional example here that you can see here is how to design 60 Hz notch filter. So for that you have a function which is called design field, and you're just defining, for example, band stop filter IIR of second order, and then you want frequencies to be between 59 and 61 Hz to be blocked, and then you're using Butterworth filter with sampling rate of f of s, and this will design the filter for you, and then you're using filt function basically to filter 60 Hz from your signal x with that design filter D. But you have some convenient app in the Matlab which helps you to design filters, general filters, any filters you want, any IIR or FIR filters based on the specifications that you want. So based on the specifications, you just open that app, put all of the parameters that you want, and it will not only design the filter for you, but it will also generate code which filtering your particular signals that you want. So it will generate all of the Matlab codes that you need to copy paste into your software just to get your signal filtered. All right? So thank you for listening.